My project of synthesis depth of field from depth estimation using mobile devices. Here is a showcase of the final framework that I developed. Given an all-in-focus image, the user can select any focal plane and adjust aperture using a GUI. Depth of field refers to the distance between the nearest and farthest object in a photograph that appear acceptably sharp. In other words, it is a portion of the scene that is in focus. A shallow depth of field means that only a small part of the scene is in focus, while a large depth of field means that more of the scene is in focus. While it plays an important role in professional photography, we can hardly see in photos taken by mobile devices such as a mobile phone. This is because the smartphone usually has a tiny camera sensor, often around 25 square millimeter. Such limited space makes a large aperture unable to be mounted, thus cannot create the same level of depth of field as DSLR cameras optically. Our system utilized data-driven approach. Firstly, we use a deep neural network with encoder-decoder structure that trained on a variety of things for estimating depth map. Then we applied edge-aware filter on the depth map to get smoother output. Lastly, we applied depth blur on each pixel of the image according to the depth. We will show each part individually. For the depth map estimation, to address aforementioned device-specific issue brought by classical depth estimation approaches, we adopt a well-trained deep learning-based depth map estimator proposed by Hashim et al. The depth map estimate by the encoder-decoder structure may contain noises that will bring discontinuity to the final output. To address this issue, we use a bilateral filter for improving the results. For computing blur parameters and merging blurs, if we assume the parallaxal and scene length approximations, there is a straightforward relationship between the circle confusion and depth. So we applied the calculation of circle of confusion in our project. And we applied truncated tent function on the depths to merge the blurs. Here we show our results. And more. So all these images are originally all in focus, and in our framework, user can select any focal point of his choice and also adjust the arbitrary aperture. One of the critical requirements for our framework is the speed, as we don't expect user wait too long to getting a rendered image with synthetic blur applied. So in this project, we were testing it on a server with NVIDIA Tesla T4 GPU and not extending to edge computing platforms such as a smartphone, but we can get a primary understanding of the computational needed. So for depth map inference, it takes around 0.5 seconds, and loading model takes 25 seconds. For blur calculation and merging, it takes roughly just 125 milliseconds. In this project, we developed a framework for applying synthetic blur for all-in-focus image that usually captured by mobile devices with tiny apertures. It is capable of selecting focal plane and configure arbitrary aperture level. Our results showed nice bokeh for randomly selected in the wild images. Though our project is built and tested with server-level computation resources, it is feasible to deploy on edge devices and developed as an application on mobile phone. Thanks for watching.